Happy Tuesday, everybody. Sorry I'm not here today. My AC broke and the repairman's coming sometime today. And it's my birthday, so if I want to stay in my pajamas all day, I'm gonna. I know, I'm 21. Be jealous. All right, so you should already have page 129 from yesterday. I need you to get that out, please. That's all you'll need from yesterday. I also need you to put a page 130. It is not a half sheet, I am just noticing, on the page that looks like a chart, kind of. It doesn't have a title, so give it a title. Solubility rules. And on the next page called Solutions Worksheet, let's give that a page 131. That's my dog barking at the neighbor who's going to work. Anyway, so make that happen for me. Got a little joke for you. It says, I like you, but we are from different states. It will never work. We just can't be together. Oh, but we can. That was your solution? Chemist humor. All right, if you remember way back when you barely knew me in September, I gave you a mixture in a cup. In that mixture, there was some sand, there was some salt, there were some poppy seeds, and there were some iron filings. And I challenged you to separate those things into different groups. That was a mixture. So this is a little bit of review. So a mixture, of course, is just anything that is just blended. It is not reacted. It hasn't formed anything new. It's not that exciting. Yes, everybody wants to tell me that Kool-Aid is exciting because it tastes yummy, but it didn't form a new substance. We started with Kool-Aid powder and water, and we ended up with both of those mixed together. No new substances appear. So now we're going to expand on that definition a little bit, and we are going to talk about something called homogeneous mixtures. You already know this prefix, you big weirdos, but this prefix means same or uniform. So if I look at something that is homogeneous or homogeneous, it's evenly blended. Like milk looks homogeneous. Like Coca-Cola looks homogeneous. Salt water looks homogeneous, meaning I put it in the same container, I stirred and stirred and stirred, and you can't see all the ingredients anymore. It doesn't mean I made anything new. It just means they are evenly blended. So the word we tend to use in our class for this is the word solution. So things that are homogeneous mixtures that are evenly blended are solutions. And they end up looking like this. And you've seen tons of solutions this year. Almost everything I give you in a beaker that's not water is a solution. Check out this one right down here, HClAq. If you remember AQ from chemical reactions, that meant aqueous. That meant something was dissolved in water. So solutions are always going to be aqueous. And so if something is aqueous and it dissolves in water, it is a solution. So this is hydrochloric acid. Hydrochloric acid is a solution. Hopefully you just took notes over that slide like it says on the top. And we've got another little picture down below. This is just one example of a solution down here. So when we say a solid goes into a liquid to make a solution, that's just one example. That's the most common thing that we think of when we make solutions, but I'm going to show you here in a minute how it's not the only solution. So the opposite of a homogeneous mixture is a heterogeneous mixture, like that mixture I gave you back in September where you had to separate everything. We were able to pick those apart easily. That means we could see the different parts And so when I look at this sample of, I don't know what this is, maybe it's sand of some sort, you can see all the different colors in that sample, which means if I gave you tweezers, it would be painful, but you could sit there and pick apart the different colors and you could make different piles of all the different components of sand. If you've ever been to Galveston, not the prettiest sand in the world, but it's better than Fort Worth sand because we don't have any. But if you've been to Florida and you've seen Destin sand, it's beautiful and it's a lot different than Galveston sand. So because they differ, that means this is a word called heterogeneous. A heterogeneous mixture, I can tell the different parts just by looking at them. It's not evenly blended and I can start to separate them easily. The reason I listed pond water as a heterogeneous mixture, this has happened to you probably before. If you've ever stepped in a puddle going in the parking lot, maybe going to the grocery store, when you step in that puddle, it looks like it's just water, but all this dirt stirs up from the bottom and starts swirling around, and your shoe gets kind of dirty, dingy, or muddy. And so pond water has lots of different stuff in it, or a rain puddle, because there's dirt that's settled down to the bottom. So you can pick the different things apart. You can see the water, you can see the dirt, you can see the mud. All of those things make pond water a heterogeneous mixture. Now, to be truthful, we don't have a lot of heterogeneous mixtures in chemistry. We're going to camp out on those homogeneous mixtures or those solutions from the previous slide. So hopefully you got a couple of things down. Don't worry, it doesn't need to be perfect. Let's just keep moving on. So how do we make a mixture? There are some vocab words that we need you guys to know at this point. You already know the word solution. We just talked about it a moment ago. But a solution has two different parts. A solution ends up being in an overall single phase, which means I look at it and I say, oh, that's a gas, or oh, that's a liquid. Most solutions, when you hear the word solution, you think liquid. Those are not the only types of solutions. And so in every type of solution, however, there's two parts. There's what we call the solute, so write that down. It's the guy that is being dissolved. So in our example that we love to talk about, this would be the Kool-Aid. Kool-Aid is a solute. Sorry, my 4-pound dog thinks she's a gremlin. Anyway, so Kool-Aid would be the solute, and the thing doing the dissolving, that is what we call the solvent. Whatever you're pouring it into typically is your solvent. We like to say that what you're pouring it into has the greater amount. So in this case, it would be the water. And the Kool-Aid, there was just a little bit of it. So it was the solute. And so in this example up here, this would be the Kool-Aid. And this would be the water. So yesterday you read that water is the universal solvent, which we'll talk about in a little bit as well. And so that's what that means, is that that's the container that you're pouring your solute into. And so this just shows, this picture at the bottom just shows a little bit of the interaction that occurs when a solute goes into a solvent and starts to disperse within that container and mix evenly, so it's evenly blended and you can't see it anymore. So this is what I was talking about a moment ago. Not everything in your world is a liquid solution, contrary to popular belief. And so when we look at a solution, we have to look at what phase of matter is our solute in, what phase of matter is our solvent in. This is the one down here that you're most accustomed to. A solid gets dumped into a liquid like sugar water or salt water, and it dissolves. But let's talk about some other interesting ones. Up here I have a picture of soda. And so soda, that is carbon dioxide getting dissolved inside of liquid to make a carbonated beverage. Oh, I thought you would appreciate this picture a little bit right here. Don't drink until you're 30. Hangovers are overrated. And so wine and alcoholic drinks, those are liquids, dissolved in liquids. And so all of those drinks can be attributed to solutions in chemistry mixing. If you've ever had a filling for a cavity, that is another kind of solution that is a liquid actually dissolving in with a solid. It used to be that they used mercury in those fillings, and then they would mix it with silver, and they would liquid mercury, put it down into the solid silver, mix it up, and then inject it into your tooth for a really, really hard substance. Anymore, they're tooth colored. They're not silver anymore. So you guys, if you've ever had a filling, you don't look like you have the little silver caps in your teeth like us old people do. And then one of my favorite ones to talk about is this bottom one, a solid solution. We get two solids really hot like metals, and we blend them together, and we make really, really strong substances like steel or 14 or 10 karat gold. And we make things like jewelry and skyscrapers and school buildings out of these really, really strong substances. We call these alloys. We talk a little bit about alloys in AP chemistry and why they work, but basically it's you take something really, really small like carbon, and you fill in the gaps of something really, really large, like iron or lead, and you put those tiny carbons in between them, and it strengthens your sheet of metal and gives you a really, really sturdy building. And so my Aggie ring is really, really sturdy. It's not going anywhere. I can bang it on the table and it won't get dented because it is a mixture of metals to make it stronger. So all I needed you to get from that page is that there are different types of solutions. If you have a couple of examples, that's all you need. You do not need specifics from this. So, like we said yesterday, water is called the universal solvent because he is polar, which we talked about the Mickey Mouse shape, and that there is a positive side and a negative side to this water. So because there's so many opposites floating around in that beaker, there's a lot of attraction, and it can easily dissolve many substances. And so if you check this out, notice the arrangement of all of these water molecules. That was really interesting. Sorry about that. Notice the arrangement of all of these water molecules and how all of the oxygens have planted themselves all right next to that sodium. That's because that sodium is positive and opposites attract. And we discussed yesterday how the oxygen side of water was negative. Well, over here, they didn't come out and tell us what acetone was, but notice how all of the hydrogens line up and surround that acetone. Well, if we know that the hydrogens are positive, then we know that they're attracted to something negative on the outside of that acetone molecule. So the way something dissolves is we know that molecules, when they're in that beaker, are going in continuous motion. So they're nonstop moving. Everything happens because of collisions. We talk about that word a lot in AP as well. And so they have to explain on the AP exam why things are happening, not just what happens or show me the math of what happens. They ask them a lot of justify your answer questions. And so they want them to explain that these water molecules over here in this beaker are in constant motion. And when they collide with things that you put in the beaker, they start to break them apart, or they start to surround them and hide them, like in this example. And so they're not visible anymore. And so when we surround salt ions with water, it looks like the salt disappeared, but we know it's still in there because you can taste it. You can evaporate out the water and the salt will reform and come back together. So the salt is in there. It's just in ion form instead of solid form. But sugar is not ionic. And so when you put sugar down into water, it doesn't break up into tiny pieces. It stays as a whole molecule. And then the water surrounds that whole molecule and it hides it for you. You can't see it, but it's in there. So the way we dissolve salt and sugar are kind of different. But in both cases, they're surrounded by water because of the polar nature of the water molecules. If you'll notice when you're looking at this bottom picture, you can notice that the opposite sides of the water are attracted to the opposite type of ion that was dropped in solution. All these little sodium ion. And so the negative side of water always is going to surround the positive cation. If you remember, cation, the T in the middle, meant something was positive. And so the negative side of water is attracted to the positive part. If this was salt, sodium chloride, so the water down here is attacking the salt molecule when we drop it in the water. And so the negative part of Mickey Mouse up here, all these little pink guys get a negative charge, and then they are I have no idea what I keep hitting the wrong button, sorry. And so this is pretty common sense, but I just want to make sure you understand because you're going to see some questions about this later, and I want to make sure you happening. So opposite must be true. The positive side of water is surrounded by anions, and anions, if you remember, the N stood for negative. So opposites attract, analyze that picture, figure out what's going on. If you've got a negative in the middle, that means you've got positives surrounding him and hiding him in the water. So that's the process called solvation or dissolving, and that is what's going on with a salt molecule. So remember a minute ago I said sugar's a little bit different. There's the fancy word for sugar. So this would be a whole blob of sugar, or a sugar, not really a crystal, but if you put a lump of sugar or a sugar cube down into water, water's going to do the same thing. Water's going to come up and attack this big lump or this big blob of sugar. But the way that it's different is it's not going to separate it into individual ions like it did with salt. Notice this sugar molecule is going to stay intact. And it's kind of hard to see, but that's the sugar molecule on the inside circle. Here's the 4 water molecules coming to attack it from all directions. All it was able to do was to break apart this whole molecule, another whole molecule, another whole molecule, another whole molecule. So if something is covalent, and if something is polar, it will not ionize. So what will it do? It breaks off into whole molecules. And it will dissolve. So some kids think because it's not ionic, it won't dissolve, and that's not true. Sugar loves to dissolve in water. Frankly, it's way easier to dissolve sugar in water than it is to dissolve salt. Salt's annoying. Salt does not dissolve well in water. Try it at home. If you put a teaspoon of salt in boiling water, it's going to take forever for that to go away. If you put a teaspoon of sugar in water, it's going to basically dissolve instantly. And so sugar loves to dissolve. It just is going at it from a different angle. So this brings us to something huge. Make sure you write this down. So write down in your notes somewhere, like dissolves like. Here's what this means. In regards to polarity, we call this the nature of the solvent. If your solvent is polar, what does it like? It likes things that are also polar. So polar likes polar. So what else does that mean? That means if I am polar, what do I not like? I do not like things that are nonpolar. So this is why sometimes you go to mix 2 substances and they just won't mix. And it's because they have opposite polarities. And if you remember, when we talk about things being polar like water, if you put something that's polar like water with a positive and negative into something that's nonpolar, something that's nonpolar has no charges. So when the water goes hunting for opposites, it doesn't even see this thing that's nonpolar. It's like it doesn't even exist to the water. So the water completely ignores it and walks on by. And so that's why you get things that separate, like salad dressing, like oil and vinegar, like oil and water. And so not everything will mix, and it's because of polarity. So let's take a brief recap here, because this is where kids tend to struggle a little bit, because we haven't done this since November, December. So when we talked about polar versus nonpolar, I just gave you a couple of examples. We know polar means opposite. My parents are polar opposites, and they still got married and had me. All right? Nonpolar means everything is even or equal. There's my killer dogs again. And so if you look at formaldehyde, CH2O, we tend to give you the names and the symbols, like formaldehyde, like carbon dioxide. And we kind of expect at this point that you can eyeball it, or you can sketch it out in your head and say, oh, carbon's always in the middle, but there's going to be two H's, but only one O, meaning when this thing plays tug of war, it is not tugging equally. So because it is unequal, this guy is playing tug of war. This little arrow saying oxygen has a higher electronegativity and is pulling harder, so this guy is polar or unequal. The carbon dioxide, however, goes to play tug of war, and they're pulling equally in both directions, and so therefore he is nonpolar. So worst case scenario, we give you the formula, and you have to draw the molecule, just like we used to. Find the available electrons, divide by 2, and sketch out your molecule. Best case scenario is we're going to give you a picture like we did down here. These are not the same molecules. These are different molecules. But when I give you this picture, we're expecting you to see that, oh, when I chop this through the center atom, the top looks very different from the bottom. If you remember why, there must be some lone pairs sitting up here, making this side negative, making the hydrogen side positive. But when I look at this atom over here, all three of these are equivalent, meaning they're pulling equally in all directions, making him nonpolar. I'll post this video to my webpage, and I'll send it out and remind, so in the event that you need to watch this part again or write that down, you'll have it available. So this is big right here. These are basically the rules for like dissolves like, and it goes like this. So the first thing I would write down is polar solvents. Polar solvents will dissolve things that are polar, because like dissolves like. But here's what you might not expect. They will also dissolve things that are ionic. If you remember, ionic means metal, non-metal. So this means they're opposite. Well, polar means opposite. So when a polar comes in to look at an ionic, all it notices is that it has opposite charges, so it's going to treat it just like it treats a polar molecule. Opposites attract. And so polar solvents will dissolve polars and ionics. This is why water will dissolve salt. Salt is ionic. And water will dissolve sugar. Sugar is covalent, but we know that sugar is polar, because when we looked at that molecule earlier, it was very lopsided and crazy looking, and so it was not pulling equally from all sides. If something is a non-polar solvent, what are they going to like? Things that are non-polar are going to also like things that are non-polar. If you remember, non-polar means Everybody is equally distributed. There are not any positive and negative charges. And so this would be like gasoline dissolving in oil. So let's take a brief moment to talk about this. If oil is nonpolar and water is polar, will they mix? And the answer is no, because they are not alike, so therefore they do not like each other. So that is huge. Remember that we had this discussion. It's not really a discussion. You're listening, hopefully. I'm watching you. All right, now here's the weird part. We don't teach this to on-level kids. We save this for pre-AP because it's a little confusing. So here goes nothing. If something is an alcohol, in chemistry, all that means is that it's usually a CH compound with a hydroxide at the end. So it's an organic molecule with carbons and hydrogens, and there's an OH somewhere at the end. And so methanol, which is, trying to think if I used methanol this year. Oh yes, when I made the whoosh bottle and I poured some alcohol into the big 5-gallon jug and I lit it on fire, that was CH3OH. That is methanol. And so all alcohol means is a carbon hydrogen CHO compound with an OH hydroxide at the end. So they are considered polar because of that hydroxide group. So they will mix with polars, but here's what's really strange. They'll also mix with nonpolars, but they will not mix with ionic substances. So methanol, alcohol, will dissolve in water. It will dissolve in gasoline. But if I put salt into the methanol, it will not dissolve. So alcohols do not like ionic substances. They only like polars and nonpolars. So they don't really follow their own rule. And so it's a little bit strange. We will practice more when I get back, but at least you have it in your notes and we'll talk about it later. All right, last part for today. Find page 130. If you didn't put a title on top of this yet, please put solubility rules. Solubility rules. So I have two new words to introduce to you today. One is the word soluble. So the word soluble means it will dissolve. And his symbol for it, symbol for will dissolve is AQ. That means it's aqueous, so everything mixed. You can't see the different parts. They went away. The word down at the bottom for insoluble, you can take a guess. Insoluble, you got it. It won't dissolve. So you put them in the same container, something sinks to the bottom or floats on the top, and it won't dissolve at all. And so when this happens, you put an S. S does not stand for soluble. Be careful, be careful, be careful. S stands for a solid. PPT, which is my abbreviation for precipitate. Precipitate. So let me show you how these solubility rules work. What we're going to do is we are going to do these 6 examples. So it wouldn't be a bad idea on page 129, your notes page, to put solubility rules and to put these 6 examples that I'm about to do with you. But we're going to reference this chart at the same time. So we're going to multitask, all right? So the first one I need you to write in your notes is copper nitrate. This is copper Roman numeral 2 nitrate. Here's how this chart works. Look up the anion, the negative ion. So you look up nitrate. You find him. He's right there. And you say, what list is nitrate on? Well, he's on the soluble list. But then we have to check, does he have any of these exceptions? Thank goodness the answer is no, there are no exceptions. So the answer to copper nitrate is he is soluble. The symbol for soluble is AQ. So we're going to put AQ next to copper nitrate. So here's the cool thing. I've been doing this for 1,000 years because I'm as old as a dinosaur. I know that all nitrates are soluble, which means they mix with water well. So when I have to choose a compound for a lab, what am I going to do? I'm going to pick some nitrates because they always dissolve and go right down the drain. So that's kind of nice. Let's do another one. Ready? Write the second one in your notes. Magnesium carbonate. Magnesium carbonate, we're going to look up the anion or the carbonate. We're going to find out that it's on the list on the bottom, which is the insoluble list. But wait, we have to check the exceptions. Is he attached to NH4? And the answer is no. Is he attached to an alkali metal? Well, that depends. I forgot what an alkali metal is. Anybody remember? Huh? An alkali metal, write this on your chart, then you won't forget. Right above there, write group 1. Everybody in group 1 is soluble. So I can do anything with lithium, sodium, potassium, rubidium, cesium, and pour them right down the drain. They're always soluble. So since this is magnesium, he is not in group 1. And so he is not an exception. So he is considered insoluble. So he's going to get an S. So then we keep going. Our third one. So we look at the chlorine ion. Here he is. We say he's attached to ammonium. Is that an exception? Nope. So he's on the soluble list. AQ. Sodium hydroxide. Look up the hydroxide. Find him down here on the insoluble list. Is it an exception? Well, it's not NH4, and it's not calcium, strontium, or barium, but it is an alkali metal. So since it's an exception, it really belongs on this list. So we're going to call sodium hydroxide aqueous. Because if you remember what I said a second ago, everybody in group 1 is always going to be aqueous. So we've got another hydroxide right here on number 5, magnesium hydroxide. So we're still down here at the bottom for hydroxide. And then let me erase and make sure we don't have any exceptions. So it's not ammonium, and it's not any of those other guys, and it's not an alkali metal, so this one is insoluble, so he's going to get an S. Last one, pay attention. Lead chromate. We look up chromate. We find what list chromate is on. Oops, sorry. Having trouble with my tools. Chromate is down here. He is insoluble. He is attached to lead, not an exception. So he is also going to be a solid. So the chart is awesome. You have to be aware of exceptions. Basically, all of these exceptions up here belong on this list. All of these exceptions down here belong on this list. It's a train wreck. It's a mess. There's other lists out there and other ways to look at this. But the STAR test had this chart that we've continued to use since our test went away. And it's pretty handy. It's pretty helpful. So if you're lost, we'll help you. Don't worry. Last slide. Here it comes. All right, so now that we know all of this information, your brain should be a little bit mushy, lots of stuff. Now what we're going to do is we are going to predict products just like we did in the chemical reactions unit, but now we have to determine who is the precipitate, and I don't get to do the reaction in real life. I have to just know by looking at my partners. Good news, everybody's a double replacement. Nothing weird, nothing hokey. I literally just switch my sodium and my barium, and I crisscross. So write this first one in your notes. Write this first one in your notes. Sodium sulfate, I crisscrossed my two, reacts with barium chloride, crisscrossed bariums 2, to make new partners. Now on the other side, I've got barium plus 2, hooking up with sulfate minus 2. The 2's cancel. And my next product should be sodium plus chlorine minus. So at this point, you need to look up on your solubility chart what is the phase of matter for all of these compounds. I'm sorry, what is the solubility for all of these compounds? Well, in a double replacement, the reactants are always aqueous. So I can just go ahead and label those. If you don't believe me, go look them all up on your chart. You're going to find that all of your sodiums, because they're in group 1, are soluble. And you're going to find that chlorides are mostly soluble, a few exceptions, but barium is not one of them. So then when I come to the other side, I start looking up my anion. Sulfate, if you go find him, he is on the insoluble list. Barium is not an exception to sulfate, so we're going to put parentheses solid. And then if we go look up chlorine on our list, it's a very terrible Cl, but that's what that's supposed to say, Cl. So when I look up chlorine on the list, chlorines are on the soluble list. Sodium is not an exception, and we said a minute ago that all group 1s are always soluble. So he's going to get an AQ. We need a 2 in front of that salt to balance, but basically we just predicted the products, and we predicted that our barium sulfate was going to be our precipitate, and we didn't have to do the reaction to get that evidence. We have solubility rules that will tell us that in advance. It doesn't matter what order you do these in, but I'm going to do the third example next. So we're going to write some potassium nitrate reacts with some iron 3 chloride. Aqueous, aqueous. So my potassium and my iron are going to switch, and I'm going to get iron crisscross the 3 to chlorine, so he's going to bring that with him to the other side. Hooking up to nitrate. Nitrate's a -1. Crisscross that 3. And potassium hooking up to chlorine. +1, -1, they cancel. Bloop, bloop. So if you remember, all group 1s are soluble. So I can put an AQ right next to potassium chloride. Both of my reactants are aqueous solutions, always. So I can put those down. So now I'm just trying to find out what this is. So I look up my nitrate. I know what you're assuming. Some of you are like, oh, that must be the solid. That must be the precipitate. Except this is on the AQ list. and there are no exceptions. So in this reaction, and this happens sometimes, in this reaction where everything is aqueous, that means everything stays dissolved. Did you really create anything new? And the answer is no. So really, none of this is the answer. The real answer is NR for no reaction. Everybody say hi, Chloe. She's ferocious, I tell you, all 4 pounds of her. So the last one, we are done for the day. We've got some chromium nitrate. I did not balance the bottom reaction. There wasn't a reaction to balance, and so, oh well, if it bothers you completely, please go back and put a 3 in front of the potassium nitrate. Oh, there's my lightsaber. Isn't it cute? I clicked the wrong button. All right, so go back and put a 3. I don't know how to move these tools. They're in my way. Anyway, a 3 in front of the potassium nitrate for sure, and a 3 in front of the potassium chloride, but not necessary. There's no reaction. So again, to our third reaction, chromium nitrate reacts with ammonium sulfide. Since it's a double replacement, my reactants are aqueous. We're going to flip them and end up with ammonium nitrate. Look what we said a minute ago about nitrates. Nitrates are always soluble. So he's going to get the AQ. And chromium plus 3, sulfide minus 2, crisscross. We look up sulfide on our chart, the S. When we look up S on our solubility chart, we find out that he is on the insoluble list. So he's going to get the S. I don't know if you ever saw the movie Erin Brockovich, but it was about hexavalent chromium being in the groundwater and how it's dangerous. And so this is chromium with a 3 charge, and it is not near as bad for your body and for you as hexavalent chromium, which would be a CR with a positive 3 charge. And so it is not balanced. Horrible. So we're going to go back and make that happen. We're going to put a 3 in front of the ammonium, a 3 in front of the ammonium. I lied. No, I didn't. A 6. Oh, we're going to put a 6 in front of this ammonium. Yep, that's where I lied. And then we're going to put a 2 in front of this chromium nitrate over here. Sorry, it's been kind of a mess trying to hurry. I know I took up most of your day. Now, if you'll get out page 131, that is your homework for today. So get as much of it done before the bell rings today. Your lovely guest teacher is going to come around and beat you with a stick and make sure that you are focused and not on your telephone, not necessary, and that you are working swiftly to finish as much as you can. Do the ones that you know how to do. Come back with questions for tomorrow. A blank paper is not acceptable. You know this. Have a great day. Happy birthday to me. Bye.
Stop.